Hi everyone, today I'll talk about the IEMOCAP dataset, which is used for analyzing emotions in speech. First, we'll start with an introduction to understand what this dataset is and why it's important. Then we'll discuss how the data is pre-processed. This includes cleaning, extracting features, and preparing it for analysis. Next, I'll explain the technologies used, such as AI and deep learning, which help classify emotions accurately. Finally, we'll look at the applications of IEMOCAP in areas like virtual assistants, mental health analysis, and emotion-aware AI systems. The IEMOCAP dataset is used to study emotions in speech by combining multimodal data, including audio, text, video, and motion capture. Speech and text help analyze tone and words, while motion capture tracks facial expressions using markers to understand subtle emotional cues. These elements allow AI systems to detect emotions more accurately. The dataset plays a crucial role in improving virtual assistants, healthcare applications, and human-computer interaction, making technology more emotionally aware and responsive. This dataset consists of 5 dyadic two-person sessions where actors engage in scripted and spontaneous conversations to capture emotional expressions. These interactions are recorded using audio, video, and motion capture to analyze emotions in real-world dialogues. Researchers use this dataset to study how people express emotions through speech, facial expressions, and gestures. The collected data is then annotated with different emotional labels, helping AI models improve emotion recognition for applications in virtual assistants, sentiment analysis, and human-computer interaction. The emotions using 3 key data modalities: speech, video, and text. Speech data helps analyze tone, pitch, and emotion in voice, while video captures facial expressions and gestures for a deeper understanding of emotional cues. Text transcriptions provide valuable context by recording spoken words and their meanings. These multimodal data sources work together to improve emotion recognition in AI, enabling better applications in virtual assistants, mental health analysis, and human-computer interaction. Emotions play a crucial role in communication, and understanding them helps improve AI interactions. This system categorizes emotions into 6 types: neutral, angry, sad, happy, frustrated, and excited. Each category captures different expressions, tones, and gestures, making it possible to train models for emotion recognition. Pre-processing is a crucial step in preparing data for analysis. It involves processing video frames, cropping faces, cleaning data, and creating structured data frames. To ensure accuracy, the data is shuffled and then split into training, validation, and testing sets. Each set is resized and rescaled, with training data sometimes undergoing augmentation to improve model performance. These steps help create a clean and well-structured dataset for training emotion recognition models effectively. Emotion sensing relies on 3 main modalities: questionnaires, physical cues, and physiological signals. Questionnaires like PANAS and SAM collect self-reported emotions. Physical cues include facial expressions, speech, gestures, and body posture, which are analyzed to detect emotions. Physiological signals such as EEG, ECG, respiration, skin temperature, and eye tracking provide deeper insights into emotional states by monitoring bodily reactions. Combining these methods enhances emotion recognition for AI, healthcare, and human-computer interaction. Video-based emotion detection tracks facial landmarks, gestures, and movements to analyze emotional expressions. By studying facial muscle activity, eye gaze, and posture, AI models identify emotions like sadness, happiness, or frustration. When combined with speech and text, these systems improve accuracy in emotion recognition, making AI interactions more natural. This technology is applied in human-computer interaction, mental health analysis, and AI-driven communication systems, helping create responses that align with human emotions, improving engagement and support in various fields. Audio pre-processing is essential for emotion recognition, involving feature extraction techniques like mel-frequency cepstral coefficients, MFCCs, pitch, and energy analysis. Raw audio files undergo noise reduction and normalization to enhance clarity before extracting meaningful patterns. These processed features help train AI models to detect emotions in speech, improving applications in virtual assistants, emotion-aware AI, and sentiment analysis. High-quality microphones are essential for speech emotion analysis, capturing voice signals with clarity and precision. These recordings help extract key features such as tone, pitch, and intensity, which are crucial for recognizing emotions in speech. Advanced audio technology ensures that even subtle emotional cues are detected, improving applications in virtual assistants, sentiment analysis, and human-computer interaction. High-resolution cameras are used to track facial expressions and gestures, capturing subtle emotional cues in real time. By analyzing movements, eye contact, and facial muscle activity, video data enhances emotion recognition accuracy. This technology is essential for human-computer interaction, behavioral studies, and AI-driven emotion analysis, making systems more responsive to human emotions. The Vicon motion capture system uses 8 cameras to track facial expressions and body movements with precision. Subjects with markers provide detailed motion data, while unmarked subjects help analyze natural behavior. This setup improves emotion recognition, allowing AI to study gestures and facial cues more effectively. It is widely used in psychology research, virtual reality, and effective computing, helping to create more realistic simulations and enhance human-computer interaction in various applications. Motion capture technology uses infrared sensors to track facial movements by detecting small changes in muscle activity. This system analyzes expressions by mapping facial points and comparing tracked motion with ground truth data, reducing errors for accurate emotion recognition. It is widely applied in AI-driven emotion analysis, virtual reality, and behavioral research, improving real-time human-computer interaction. By capturing detailed facial expressions, this technology helps create more responsive AI systems and enhances digital interactions across various fields. Motion capture, MoCap markers are placed on an actor's face to track facial expressions with high precision. These markers help capture micro-expressions and muscle movements, generating detailed motion data for emotion recognition. The collected information is used in animation, AI-driven emotion analysis, and virtual reality, improving realism in digital interactions. Machine learning models such as CNNs, RNNs, and transformers are used for emotion classification by analyzing speech, facial expressions, and text. Convolutional neural networks, CNNs, extract spatial features from images, while recurrent neural networks, RNNs, process sequential data like speech. Transformers enhance performance by capturing complex relationships in multimodal inputs. Multimodal analysis enhances emotion recognition by integrating speech, facial expressions, and text. By analyzing tone, visual cues, and linguistic patterns together, this approach improves accuracy in detecting emotions. Such integration is widely used in AI-driven emotion recognition, virtual assistants, and human-computer interaction, making systems more responsive and emotionally aware. Dyadic conversations provide a more natural and realistic way to capture emotional expressions compared to isolated speech samples. The dataset includes both spontaneous and scripted dialogues, combining controlled interactions with real-life speech patterns. This approach enhances emotion recognition, AI-driven communication, and human-computer interaction, making systems more adaptable to real-world conversations. Speech emotion recognition, SER, enhances AI assistants like Alexa and Siri by detecting emotions in voice signals. It involves feature extraction from time and frequency domains, followed by machine learning models like SVM, decision trees, and neural networks for classification. This technology enables AI to respond more naturally and adaptively, improving user experience in virtual assistants, customer service, and mental health applications. Virtual assistants benefit from emotionally aware AI, enhancing human-computer interactions. By recognizing emotions through speech and facial expressions, these AI-powered systems can respond more naturally, adapt to user moods, and improve engagement. This technology is useful in customer service, therapy bots, and smart home assistants, making digital interactions more intuitive and human-like.